Thank you, Federico, to give this second seminary, and you will speak about
climate time series.
Oh, that's so I let you begin, and I record the talk. So thank you everyone to attend, and to the other which will see the talk online. Thank you.
Okay, so thank you, Paul. So thank you to all to attend this seminary. So I'm Federico Maddanu, and I'm a postdoctoral researcher at the University of Cergy under the ECODEC project by Professor Paul Giucano. So today I would like to discuss to you a new process that actually is not really new, because has been introduced in the literature in the 80s, but let me say that since today it has been very little investigated in the literature. Well, this process is able to capture the empirical features of long memory time series, even though the process exhibits theoretically short memory. Therefore, it can be used as an alternative tool with respect to standard long memory process to forecasting and analyze time series characterized by elevated persistency, in particular at the long run frequency. So we know that long memory models have been widely considered, for instance, in the geophysical literature, in order to investigate on the dependent structure of many climate time series. So according to Baran in 1994, we say that the stochastic process exhibits long memory if the autocovariance function is not absolutely summable, or equivalently if the spectral density is unbounded at some frequency in 0 pi. Otherwise, we said that the process is short memory. In this paper, we focus on the analysis of the 3 climate time series where the persistence in the data is mostly concentrated at the 0 frequency. The first series concern yearly Central European summer temperature reconstruction based on Austrian Alpha 3 rings data, and other 2 time series are yearly 3 rings records. So maybe you can remember from your childhood that the age of a tree could be found by cutting the tree and then counting its rings. Moreover, the rings width can be used to estimate past temperature or precipitation over the lifetime of the tree, such that we can learn from that about the climate history for hundreds and sometimes also thousands of years. Here in this slide, I show you the 3 climate time series, and as you can observe from the periodogram, the persistency in the data is almost totally concentrated at the long run frequency. So a possible candidate in order to fit this data could be the very famous fractional noise process introduced by Oski in 1981 and by Handel in 1986, which is given by equation 1, where epsilon t is a white noisy sequence, and where the process displays long memory if g belongs to 0 and 1/2, such that the spectral density is given by equation 2, and it results to be unbounded at the 0 frequency. Let us observe that the fractional noise process can be generalized by a larger class that is denominated the class of fractional equal root autoregressive moving average processes, or in short, FerARMA process, that are the main object of this paper. And this kind of processes encompass both long memory and short memory processes as a special case. So the class of a FerARMA process could be defined by the equation in 3, where the process results to be basically stationary and invertible if the roots of the autoregressive moving average polynomial phi z and psi z lie outside the unity circle. while the parameters d1 and d2 are fractional and belongs to the interval 0, 1. Notice that from 3 we can obtain as a special case a standard ARMA PQ process just by setting d1 and d2 equal to 1. And we can also obtain a long memory process if we set, for instance, d1 in the opening interval 0, 1, and we assume for a unit root in the autoregressive polynomial. Our purpose basically in this paper is to introduce the FerARMA class as an alternative way to fit and forecast highly persistent time series. Well, in our context, we will focus on a particular special case of free that is obtained by restricting the parameter set of the order of the autoregressive and moving average polynomial to the set of 0 and 1. So we focus on the process given by equation 4, which results to be second order stationary with the short memory for any value of d1 and d2 in the interval 0, 1, which is opening 0 and closing 1, and for each value of phi and psi in the interval 0, 1, closing 0 and opening 1. Notice that also from 4 we can have a long memory special case if we set, for instance, phi equal to 1, d2 equal to 1, and if we assume d1 lower than 1/2, in this case we have a simple fractional noise with moving average over the 1 errors. Well, so let's give some comparison between the FerARMA class of process and long memory processes. So we have, for instance, that the FerARMA process results to be stationary also for values of d larger than 1/2. This allows for the support of the Durbin-Levinson recursion in the computation of the best linear predictor, because recall that long memory processes are usually non-stationary for d greater than 1/2. As a consequence, we have that the FerARMA process displays a bounded and continuous spectrum, allowing for a central limit theorem of the Whittle estimator under less restrictive assumption with respect to the asymptotic theory on long memory models given in Fox and Taku 1986 in the stationary case, and given by Velasco and Robinson 2000 in the non-stationary case. So a special case, a very interesting special case of the FerARMA class is the so-called FerAR or Spolia process, which is given by equation 5. It has been introduced initially in the literature by Spolia et al. 1980, and more recently it has been formalized in Paris 2003. So this process results to be stationary if phi belongs to the open interval 0, 1, such that we have a spectral density that result to be bounded and given by equation 6. And we have an autocovariance function that could be that is given here by equation 7 in terms of the gamma z, that is the Euler gamma function, in terms of f, that is the hypergeometric function. Notice that both the autoregressive over the 1 process and both the fractional noise process are a special case of 5. For instance, if we set d equal to 1, we obtain an autoregressive over the 1 process, and if we set phi equal to 1, we obtain a standard fractional noise process. So to investigate about the difference in the persistency between these 3 models could be of some interest. Therefore, here we investigate on the persistency of this process by considering as a measure of persistency the speed at which the impulse response function vanishes to 0. The impulse response function is defined as the sum of the coefficient of the moving average representation of the process. So in this figure, we consider a switchable parameter set, and we see that the coefficient of the moving average representation of the Spolia process, let's say, decays lower with respect to the coefficient of the autoregressive over the 1 process, that are the yellow bar, and decrease faster with respect to the coefficient of the low memory fractional noise process, that are the red bars. So basically, we see here that the Spolia process is like something of a hybrid between short memory and the low memory process for given a switchable parameter set. So another interesting case of the FerARMA class could be just the Spolia process with the moving average of over the one errors, which is given by equation 8. And as before, it has a bounded spectrum given by equation 9 and the autocovariance function given by equation 10 and 11 in terms as before of the Euler and hypergeometric function. Well, let's now consider the issue of estimating the parameters of the FerARMA class. Here we consider the standard Whittle and exact likelihood estimation. In equation 12, we report the function, the exact log likelihood function, where sigma t is the variance covariance matrix, and theta is the vector of the parameters. And because the inversion of a large dimensional covariance matrix could be laborious, we compute here the inverse of sigma t via the Durbin-Levinson recursion. So basically, according to Brockle and Davis in 1986, we can compute the best one-eyed linear predictor of yt plus 1 in terms of yt minus 1, yt minus 2, and so on, given via this following autoregressive order n representation, where the vector of parameter phi is the solution of the Euler-Walker equation and can be computed recursively via the Durbin-Levinson recursion, which is given by this system of equation here, where the parameters phi mm are the partial autocorrelation, gamma k hat is an estimate of the autocovariance function, and the nu t is the one-step ahead mean square prediction error. At the end, via the Durbin-Levinson recursion, we can compute, as we said before, the inverse of the variance covariance matrix according via the following matrix decomposition. So on the other hand, the Whittle likelihood is an approximation of the exact log likelihood where the covariance terms in the time domain are substituted by spectral terms in the frequency domain. It is given here by equation 13, where F is the spectral density of the process that of the model that we are estimating, and I of omega is the periodogram. Well, the main advantage of the Whittle approach with respect to the exact likelihood estimation is that the computation may be simplified considerably in the via the Whittle method. It also follows from the standard asymptotic theory by Hannan in 1973, which allows for a standard ARMA P-Cool process, that in the case of the FerARMA class, we have that the Whittle estimator theta hat, which maximizes the function 13, results to be consistent in the probability, and it results to be asymptotically normal distributed, according with the following theorem that could be proved just by considering that the standard assumption present in Hannan 1973, which holds for the FerARMA class of process, because as we said before, the FerARMA processes exhibit theoretically short memory. Well, in the following, to prove what we said theoretically with the previous theorem, we implement a Monte Carlo experiment simulating 1000 times a sample size of length t realization from the Spolia process, and then we proceeded to estimate the model via both the Whittle and the exact likelihood approach. Our purpose here is to compare the two approaches in estimating the parameters of the Spolia process. So in this table, I report the result in terms of the bias of the parameters, considering a large sample size of t equal to 2500. And we see here that basically the two approaches performs almost identically. So therefore, the Whittle estimator could be used instead of the exact likelihood estimator for a large sample size. Also notice that we have here a large bias when both the G or just one of the G and phi parameters are quite low. Well, this is because both the two parameters in the case of the Spolia process are able to describe the memory of the process, and so they could come into conflict with each other when one or both of them are small. And also notice that here we have a sort of identifiability problem, because if we back to the equation of the Spolia process, Here we see that as D or phi approach to 0, then we have that YT approach to be a white noisy sequence. Okay, so it should be also interesting to observe how the Spolia process is able to is able to fit the empirical features of the property of low memory. So what I mean is that how works the Whittle and the exact likelihood estimators when we are simulating as a data genetic process a Spolia process which is approached to be a low memory process. So if we assume as a true value of the phi parameter very close to 1. So basically, we repeat the same experiment by considering a phi parameter very close to 1, in the sense that in this case, the Spolia process tended to show some long memory features. And we see that also in this case, both the Whittle and the exact likelihood estimator perform almost identically, except for the case in which we are estimating a process that is low memory under non-stationarity. That is the case in which phi is very close to 1 and d is greater than 1/2. And we see that in this case, the Whittle approach performs better with respect to the exact likelihood approach in terms of the bias of the parameters. This because of the drawback of the Durbin-Levinson recursion in inverting the variance covariance matrix when the process is close to the non-stationary region. Well, another way that in which we can consider the Spolia process in order to capture the low memory features generated by a data generating process is to consider as a data generating process a short memory process with occasional shifts in the means. So we know from the literature that a short memory process with occasional shifts in the means can generate low memory. Therefore, here we consider as simulated data, the data generated by equation 14, where we have basically a white noise plus occasional breaks in the mean. Here we have that both epsilon and HT are two normal render variables, which are independent of each other. And B high follows an ID binomial distribution, such that basically we have that the probability to have a shift in the mean is equal to P, and the size of such shift is regulated by eta T. So let's generate a sample size. Let's repeat a Monte Carlo experiment here, generating the data from the process in 14, and then let's estimate for this process both a Spolia and a fractional noise process, which is the standard low memory process. So we see here from this table that has the number of bricks increase, and as the size of the breaks increase, then we have that the Spolia process, that is here the FerARMA approach basically to the fractional noise process that is here in the bottom of the table, and basically they returns the same estimates of the parameters of the low memory parameters in particular. And for what regard the phi parameter, we see that basically the Spolia process returns a phi parameter that is pretty close to 1. So let's just summarize the result of the simulation study. So we see that for the Spolia process, the Whittle likelihood leads to accurate parameters estimates if the sample size is large, as well as the exact likelihood estimator does. Then we see that if both the phi and d parameters are we see that since both the phi and d parameters affect the memory of the process, we have that they could come into conflict with each other when either one or both of them are quite small. In this case, in fact, we have that the Spolia process tends to be more similar to a white noise sequence. On the other hand, it should also be clear that the Spolia process estimates are more accurate in the case of high persistence data. So when phi and d are large. And then we have that in approximating low memory under non-stationarity. In the case we simulate a spoliar process with the d equals 0.6, for instance, and the phi very close to 1. We have that the Whittle approach leads to very much more accurate parameters estimates with respect to the exact likelihood approach, because of the drawbacks of the Durbin-Levinson recursion in estimating the covariance matrix in the proximity of the non-stationary region. Finally, if we consider as a data genetic process and short memory process with a shift in the means, we see that basically the spoliar process approach to a low memory process as the size and the numbers of blocks increase, along with the persistency in the simulated data. Well, so let's now address the important issue if the FerARMA model is the better model in a given situation, or if a long memory specification should be preferred. In order to do this, we consider a log likelihood ratio test, where we're going to test the null hypothesis of long memory against the alternative hypothesis of a short memory specification. So basically, we rewrite the spectral density of the FerARMA specification according with the equation 15, where F1 is the bounded spectrum of a generic short memory stationary process. And basically, we consider here the statistic in 16, that is basically a Whittle likelihood ratio test, where we test the null hypothesis of long memory, which means phi equal to 1, against the alternative of a FerARMA specification, which is phi lower than 1. And we do this by computing the statistic in 16, where L of W is basically the Whittle likelihood that we see before, evaluated in the FerARMA and the low memory case. It follows from Taniguchi and Amano 2009 that the test the statistic of our test result to be under the null hypothesis of low memory, result to be asymptotically distributed as a chi-squared with 1 degree of freedom. And we can prove also this theorem by following the theory in Taniguchi and Amano 2009. So in order to prove, empirically, what we said here in theory, we consider a Furter Monte Carlo repetition, where at each trial we generate a sample size of length 1000 or 2500 realization of the spoliar process by considering a value of phi very close to 1, such that then we compute the LR statistics. Here I report the empirical density of the likelihood ratio statistic, where here the blue line, the blue density is the one which consider the lower sample size of t equal 1000, and the pink empirical density is the one that consider the larger sample size of 2500. Here, the vertical green line is the critical value, such that if the likelihood ratio statistic is larger than this critical value, then we can reject the null hypothesis of low memory. And so we see that for phi that is lower than 0.98, and if we consider the largest sample size, we see that basically our empirical density, our pink empirical density is totally on the right of the critical value, which means that we are rejecting the null hypothesis of low memory, according with our theorem. However, we can say that our test is less efficient in rejecting the null hypothesis of long memory when the sample size is smaller, for instance, for t equal 1000. Finally, in the last panel, where we consider the simulation with phi equal to 1, we see that basically we always cannot reject the null hypothesis of low memory, and that the statistic clearly exhibit the distribution of a chi-square with the one degree of freedom, as we claim in our theorem. Okay, so let's move now on the empirical illustration on climate time series. So we consider here the problem of analyzing and forecasting the yearly records of the 3 rings and temperature reconstruction time series. Our purpose here is to compare low memory models with respect to the FerARMA class that we are introducing in this paper in terms of the Spolia process, that is the FerAR here, and the Spolia process with the moving average over the 1 errors, that is denominated as FerARMA here. And we compare these 2 models with respect to standard low memory models, which are given on the bottom of the slide and are represented by a fractional noise, with an autoregressive over the 1 component, by a FEMA process that is a fractional noise with a moving average over the 1 component. And then also we consider a FerARMA process that is a fractional noise with a fractional moving average over the 1 component. So here in this table, I report the parameters estimates obtained for these for the 6 models and for the 3 time series. So what we can immediately observe here is that the variance parameter, that all the models report more or less the same value for the estimates of the variance parameters. Also, we observe that we estimate a memory parameter G that is basically around 0.5. This suggests us that we could have non-stationarity under log memory. On the other hand, we also estimate phi parameters in the FerARMA case that is pretty close to 1. Finally, what is also interesting to observe from this table is that the value of the likelihood is greater in the case of the FerARMA process with respect to the alternative long memory models. This is a first suggestion that the FerARMA class could be more suitable model to fit such climate time series. Okay, so a first question that we can do here is to test in the case of low memory if the process are if the data are not stationary or not. So therefore here we consider the long memory models and we test the null hypothesis if G is equal 0.5 against the alternative of stationarity. To do this, we just we use the Lagrange multiplier test by Robinson 1994, and we see that for all the series and all the low memory models, the test cannot reject the null hypothesis of non-stationarity under low memory. Then we also test in the FerARMA case if the phi parameters is equal to 1, which means that we are testing the null hypothesis of low memory against the alternative of a FerARMA specification. And we perform this test by using the likelihood ratio test that we introduced before. And we see that the test rejected the null hypothesis of low memory for most of the series, but not for the Arizona 3 rings series. We're gonna back on this in a bit. Here I just report some residual diagnostic that we obtain when we fit the Spolia process for this free climate time series. What we observe here is that we obtain a white correlogram. So basically there is no correlation in the residual, and also we do not see any residual periodicity from the periodogram of the residual. This suggests us that the Spolia process provide a good fit for this data. Finally, let us illustrate as the FerARMA class is able to improve predictive accuracy in a recursive forecasting experiment with respect to long memory specification. So we start by setting T0 equal to 600, and we estimated the models using the first T0 plus T observation for T equal 0, 1, and since to T minus T0 minus 1. And then we predict our process H step ahead for H equal to 1, 2, since to 20. Since we are able to compute the mean square prediction error at each H horizon. And then we will use this mean square prediction error to compare the forecasting performance of the various models. So the comparison is reported here. where the dashed blue and red line are the two FerARMA models, while the dotted line are the standard long memory alternative. And we see that for each series, the FerARMA class provided a lower mean square prediction error, especially if a long prediction horizon is considered. Notice also that our FerARMA process provided the lowest mean square prediction of errors, also in the case of the Arizona 3-ring series. And if you remember, we rejected the null hypothesis of a long memory for the Arizona 3 rings. But however, the FerARMA class, the FerARMA processes provide in the same way a better performance in terms of forecasting. So we are close to finish. So basically, just let's just have a summary of what we do with this paper. So we have that in this paper we propose the FerARMA process in its short memory specification as an alternative way to forecast highly persistent time series, as for instance the 3-ring series that we said that we see. The main advantage of such processing concerns the stationary condition, which holds also for values of d greater than 1/2, enabling for the use of the Durbin-Levinson recursion in the computation of the best linear predictor. And let me stress that this is not possible in the long memory case under non-stationarity. And we see that for our climate series, we cannot reject the null hypothesis of non-stationarity in the long memory case. Well, on the other hand, in the Spolia process, for instance, we have the possibility of regulating the persistency in the data through two parameters that are the D and the Phi parameters, for instance, in the Spolia case. And this probably provides more flexibility to the models in capturing the dependent structure of the data. Basically, we have that all these peculiarities allow to the FerARMA process to perform generally better with respect to its long memory counterparts in forecasting several kind of climate time series. This is why I suggest that the FerARMA class should be highly considered in empirical studies on data set showing elevated persistency, but for which a long memory specification maybe not be the most appropriate. And we can also investigate on this issue by using the test, the likelihood ratio test that we propose in this paper. A possible application of the Spolia process could be in climate science concerning the issue of modeling the so-called climate noise, which arises from the sampling variability of high-frequency climate variables. So a common choice in the climate literature to model the climate noise was with the autoregressive over one process, or red noise process, if you want. However, there is also several papers who propose the fractional noise or pink noise, if you want, as a better choice, since the climate noise could be related to the interaction of several other climate variables that, if we assume that they follows an autoregressive over the one process, that then we have that from the aggregation of this variable, we can it can generate long memory, according with the famous paper of Granger et al. 1980. Therefore, in such context, we can introduce the Spolia process as a possible alternative with respect to red noise and the pink noise specification. So last, let me say that this paper has been is currently under peer review in the journal Statistical Papers, and it passed the is pretty close to publication. So was basically all. Merci beaucoup pour votre attention, and that's it. So I finish. Thank you.
Merci beaucoup, Federico. Je ne sais pas s'il y a des questions. S'il y a des questions concernant l'exposé de la part des gens qui ont assisté, en dehors de Guillaume qui ne veut pas beaucoup parler. Je plaisante parce que je sais qu'il n'a pas de micro. Oui, donc s'il y a des questions, elles sont les bienvenues. Pour ma part, je trouve que c'est toujours très intéressant de te voir parler et je te remercie beaucoup de ton exposé. Voilà, écoute, donc de toute façon, je vais arrêter l'enregistrement.